Hello students, my name is Charu. I have done MTech in Information Security from NIT Jalandhar. I have more than 3 years of teaching experience and qualified GATE also. In the last lecture, we have studied the translation look-aside buffer TLB and what is the use of that, and we have practiced some GATE questions based on that topic. Now the next topic is the segmentation. So under the non-contiguous memory allocation only, we have the segmentation part. So what we have here, so first technique we studied under the non-contiguous memory allocation, that was the paging, right? Paging we have studied. What is there in paging? Paging we have fixed size pages. Fixed size partitions होती थी उसमें, and we work in the physical memory. We divide the physical memory in paging. On contrary, here in segmentation, what we do here is, here we do the variable partitions. Variable partitions can be done here, and here we divide the logical memory, or you can say that virtual memory, we divide the logical memory, right? So here we have some terms. First one is this segment table. This segment table we have that contains two columns. First one is limit and second one is base address. Okay, so it is containing the limit and base address. Here this is the logical address. Logical address we define here with the segment number, that is S, and with S and with D. So S and D make the logical address. Okay, and we have here STBR. STBR is the segment table base register that stores the base address of the segment table. That stores the base address of the segment table. And this is the main memory. We have base address here, and here we have base address plus limit. So let's see here. And this offset, the value of the offset must be equal to the, or must be equal to 0, or it can lie to 0 to segment limit. Okay, it should be equal to 0, or it can take any value to 0 to whatever the segment limit is. Okay, so here we do generate the logical address with the help of CPU. CPU first generate the logical address. Here we get the segment number and offset. Okay, so the value of offset will be compared with the limit. So it must be less than the limit value, that is offset should be less than the limit value. If that is the scenario, then we are going to add the offset value and B value, and then we go get the base address there in the main memory. Okay, so here we do the B plus D, then we refer to the main memory, that particular frame we get in the main memory. If that is not the condition, D is greater than the limit, then we generate the trap, or we can simply say that error occurs. Okay, hope this is clear to you. Let us see with the help of example. Suppose this segment number we have is 1 and this D we have is 100. Okay, so here we have segment number 0, 1, 2 and 3. Here we have the limit 200, 300, 400, 500. Here we have the base address 1000, 2000, 3000 and 4. So first it will see the segment number with the help of logical address. Suppose I have to fetch the segment number 1. Okay, 1 I am going to see. Segment number 1, what is the limit? 300. So offset value is 100. 100 should be less than 300, right? This should be the scenario. So yes, this is correct. So I will add the base address with the limit. What is base address corresponding to segment number 1? This is 2000. So B value is 2000. What is the D value? D value is 100. Okay, I simply added. So this is the base address. This will be 2000 and this is the base address plus limit, that is 2100. So I'll get 2100. So this same I can able to find in the main memory. I hope segmentation is clear to you. Okay, so let's practice some numericals based on the segmentation. So this is the consider the following segment table and segment number is given, and they have asked that which one of the following logical address will produce trap addressing the error. So this segment table is given to you and with segment number, base and length. See the previous diagram. Now this thing is given to you. Okay, and they have asked that whether the logical addresses are given in the options. So we have to check which logical address will produce the error. Okay, we'll check one by one. Let me consider the case number 1. Case number 1, what is the logical address given? LA is given. First is segment number is given and D is given. D is 430, right? So what is the limit here? So this is the base address, this is the length, or you can call it as limit. Okay, so limit is given 700. So I will compare with the offset, that is D. My D should be less than limit. Yes, it is less than limit. Then what I will do? I will simply add the base address with the offset. That which part I have to fetch in the main memory. Base address corresponding limit का base address क्या है? 0 segment का 1219 plus offset क्या है? 430, right? So it will be somewhat 1649. So there is no error. Okay, let me consider the case number 2. Case number 2, we have segment number 1. See the second option, and offset as D. So I have to compare D with the limit. This condition should be there. What is the segment number? This one, 1. What is the limit? 14. So 11 is less than 14. Yes. So I will simply add the base address. Base address get 2300 plus what is the limit? 11. And what it will be? 2311. So here also no error is there. Third case is segment number is 2 and what is the offset? 100. So SD. So D should be less than L. So what is the D here? 100. It should be less than the limit. Segment number 2. What is the length or limit? 100. So here 100 is equal to 100, but this condition should not be tolerated. It will produce trap, okay, or error. So this condition fails here, so it will produce a error. So let me consider the case number 4, where you have the logical address, segment number and offset 3, 4, 25. So what I will do, I will compare with the limit. Segment number 3, what is the limit? 580. What is the offset given? 425. Yes, it is correct. So I will simply add the base address. What is the base address? 1327 plus what is the offset? 425. It will comes out to be somewhat 175. Okay. So it will comes out to be 1752. So it is also correct. Let me consider the case number 5. Case number 5 is segment number is given 4 and offset is given 9. This is the logical address. So I have to check this condition. What is segment number 4? Corresponding limit is 96 and limit is 96 and offset is 95. Yes, this condition is also okay. So what I will do here is I will simply add the base address is 1952 plus what is the offset? 95. So it will be 2047. So where we produce the trap or error? In option number 3. So this is the correct option. So you can mark the third option as it will produce the error. I hope the numerical is clear to you based on the segmentation. Next one is segmented paging. So there is concept segmented paging. Okay, what is this segmented paging? So what we do here is we combine the segmentation with the paging for the better CPU utilization, because there are some disadvantages also in the previous techniques segmentation and paging. So we have this topic, the segmented paging. So let us understand what do you mean by this. So here the process is divided into segments. Process is divided into segments, and each segment is divided into pages. This simply you have to remember. Okay. So here the process is divided into segments and each segment is divided into pages. So we have the logical address as, here we have the segment number, then we have the page number, then we have the offset, this offset. Okay, so the logical address is the combination of this thing. So let me read the numerical based on this topic. A certain computer system has a segmented paging architecture for virtual memory. The memory is byte addressable. Both virtual and physical address spaces contains 2 raised to power 16 bytes each. Logical address also and the physical address also contains 2 raised to power 16 bytes each. The virtual address space is divided into 8 non-overlapping equal size segments. So the logical address is divided into 8 equal size segments. The memory management unit has a hardware segment table, each entry of which contains the physical address of the page table for the segment. The page tables are stored in the main memory and consist of 2 byte page table entries. Assume that each page table entry contains one valid bit, 3 bits for the page protection, 1 is the dirty bit. How many bits are available in the, if you don't know the dirty bit, you can refer the previous videos to know what is this dirty bit. So how many bits are available in the page table entry for storing the aging information for the page? So you have to assume that the page size is 512 bytes. So let me write whatever it is given. Logical address space is given 2 raised to power 16 bytes. What else is given? Physical address space is given 2 raised to power 16 bytes. Okay. And the process is divided into 8 equal size segments, right? This is given. What else is given? Page table entry size is given. What is it? 2 bytes. Okay. And page size is given. Page size is given as 512 bytes. And there is another information given to you. One valid bit is there, and 3 protection bits are there, and 1 dirty bit is there. Okay, so this information is given to you. So what you have to do is you have to find out that how many bits are there in the page table entry for storing the aging information. For this, first we have to calculate the number of frames in the main memory. How we calculate it? You can, if you don't know how to find out the frames in the main memory, you can refer the previous videos also. So it will be size of the main memory divided by page size, right? Divided by the page size. So it will be 2 raised to power 16 bytes by page size is 512 bytes. So it get cancelled with this 2 raised to power 16, 512 is 2 raised to power 9. So it will be 2 raised to power 7. Convert 2 raised to power 7. Next one is we have to find the number of bits required for finding the page table entry. What is this? We have find it out. So how many number of bits? This is the number of bits, 7. Number of bits required for finding the page table entry. How much it is? 7 bits. Okay. So what is the number of bits that we have to find out? Number of bits required for storing aging information, right? It will be equals to number of bits in the page table entry, right, in the page table entry, minus number of bits for identifying plus 1 valid bit plus 1 protection bit plus 1 dirty bit. This we have to add here. So how many number of bits in the page table entry? Number of bits in the page table entry is 16 minus number of bits for identification of page table entry. Okay, how much it is? 7 plus 1 is the valid bit, 1 is the protection bit. I think protection bit is 3. Protection bits are 3. 3 plus 1. So what it is? 8, 9, 10. So it will be 16 minus 12. What is it? 4 bits. So the answer will be, what is the answer here? What is the answer? 4. So the answer is 4. Hope this is clear to you. The segmented paging, how we do it. So next topic is thrashing. So what is the thrashing? Suppose we have this memory. Okay, we have memory. So my motive is to increase the degree of multi-programming. What is my main motive? I have to increase the degree of multi-programming, only then my CPU utilization will be increased, right? So what I have to do for increasing the degree of multi-programming, I have to bring more and more processes in the memory. The main memory, I have to bring the more and more processes. But we have some size limitation for the memory, so it's not possible to increase the degree of multi-programming to some extent, right? I can't bring all the processes in the main memory because all the processes initially are present in the secondary memory. So we have to bring that processes in the main memory. Then how many maximum processes I can run in the main memory, according to that only the degree of multi-programming can be increased. So ultimately the CPU utilization will be better. So suppose now what I have to do is, suppose there is uh, page 1, page 2, page 3 or page 4, okay, and we have processes 1, 2, 3, 4, so on, okay. Suppose I'm bringing process 1 and I'm bringing page 1 of that process 1 and page 1. Here also I am loading process 2 page 1, process 3 page 1, so on, okay. I'm just bringing the part of a process in the main memory. I'm not bringing the whole process in the memory. I'm just bringing the part of process in the main memory. So like this I have brought here the page number 1 of process 1, right? So if CPU wants the page number 2, it doesn't exist in the main memory, right? So there the page fault occurs. What happened? To increase the degree of multi-programming, my page faults are increased. Okay, so ultimately the CPU utilization will be decreased. If it is because CPU is idle, only the servicing is involved in the page faults only, बार बार update कर रहा है उसको. So the condition when the system is spending lots of time in servicing the page faults, but the actual processing is done very less, that condition is called as thrashing. So see here, degree of multi-programming is increased, CPU utilization is increased, but here the system is involved in servicing the page faults, then thrashing comes. So your degree of multi-programming will decrease and the CPU utilization will also decrease. So this is the concept of the thrashing. If a process is allocated with very less frames, right, then there will be large number of page faults. Therefore, no useful work can be done by the CPU, then CPU utilization is very less. Then long-term scheduler would try to improve the CPU utilization by loading some more processes into the memory by increasing the degree of multi-programming. That would result in the further decrease in the CPU utilization, as there will be high number of page faults followed by a increase in degree of multi-programming. If we are going to increase the degree of multi-programming, then page faults will occur. Like this I have explained in this scenario. If we are going to increase the degree of multi-programming, then it will give rise to number of page faults. If number of page faults will be increased, then system will spend its lots of time in servicing that page faults only, and the actual processing and the CPU utilization will decrease. Okay, I hope thrashing is clear to you. This is also very important topic. Okay, that's it for today's lecture. If you have any doubts, You can comment below or you can mail also. Thank you.